Welcome, everyone, to today's CDAC webinar, our series of talks on the behavior of materials at extremes. Today, I have the great pleasure of introducing longtime friend and colleague, Malcolm Guthrie from Oak Ridge. Malcolm is a high-pressure scientist with a strong interest in the synthesis and behavior of new materials under pressure, and in particular, the detailed structure of these materials in these extreme environments using both X-ray and neutron techniques. In fact, he's one of the world's experts in the technical aspects of neutron scattering, including instrument development, structure refinements, and data analysis, which he'll tell us about today. Malcolm has a master's and PhD from the University of Edinburgh, and it was actually during that time when he was a grad student that we met. After a postdoc at Edinburgh, he joined Argonne in 2008 as part of the growing high pressure activities there that we were a part of. And he joined our Energy Frontier Research Center as our neutron group leader in 2009, 2014. He moved to Lund, Sweden to help build the high pressure program at the European Spallation Source and returned to Oak Ridge in 2021 as a senior R&D scientist. And we're very glad you're back stateside and helping to move these techniques forward. So over to you, Malcolm.
Okay, thanks very much for the intro, Russ. And just to follow up on my move back to the States, I actually made a personal phase transition. I had been working essentially for most of my career on the hardware side, but now I have become a software person. And that's what my talk will focus on today. And it turns out it actually makes a lot of sense because in the world of neutron diffraction, where I'm primarily working right now, the manipulation of data from the simple counting of neutrons all the way through to the scientific result, which is the end goal, is actually quite nuanced and tricky and is still evolving. So I'm glad to have an opportunity to talk about some of that with you today. I wanted to begin by doing a brief crystallographic prelude. I'm aware many in the audience will be crystallographic experts, but some of you may not be. And probably most of you are not so familiar with time of flight neutron diffraction, which is going to be my focus today. And so I just wanted to give a bit of background, which will make it easier to follow some of the details of that. So from a very basic, fundamental standpoint, what does the diffraction signal tell us? I have a picture here of a powder diffraction pattern. This is from silicon. And as you see, it's a series of intense peaks superimposed on some kind of experimental background. And these peaks encode information about atomic structure. And to simplify things, essentially the position of the peaks is talking about the lattice, the periodic, the unit cell, which is repeated throughout the crystal. And the intensity is telling us about the structure, the basis structure within that unit cell. And a really nice analogy I like to use is to just imagine tiles on a wall. So the position of the Bragg peaks is telling us about the shape, the size of the tile, and the intensities are telling us about the pattern inside the tile. And mathematically, this is boils down to the Fourier transform, and you can loosely think of the diffraction pattern as being the Fourier transform of the real space scattering density, which will be electrons in the case of X-rays or nuclei in the case of neutrons. With the small caveat I've noted here that what we measure is intensity and not amplitude. Otherwise, things would be very simple and we'd just do a Fourier transform and we'd get everything. So of course, the real space structure is a three-dimensional thing, and therefore so is its Fourier transform. So if we want to try and quantify that, we need to do some kind of angular sampling. And so typically that will involve either rotating your sample rotating the detector or doing both of those things, or you use a powder, which is a nice trick where you have many crystallites, they have a randomized orientation, and just by hitting all of them at once with one beam, you're sampling those orientational distributions and therefore getting your 3D information. Now, let's imagine the scenario where the data we collect are perfect. We still have to consider the differences that are imposed on those data by the microstructure. So on the left here, I have Russ mentioned my PhD work when I first visited the geophysical lab and began working with Russ. At that point in time, I grew this single crystal, which is actually i6. And so when we have a sample which is like that, and it's a perfect single crystal, it's really the ideal case for a diffraction measurement. Structural solution of an unknown phase is trivial and automatic. You get complete information on the lattice and you get complete information on the structure. And as I mentioned, another approach is to use a perfectly randomized, untextured powder. And you can go very far with that as well. You can completely solve a structure, although it's a little more challenging than the single crystal case because your information has gone from 3 dimensions to 1 dimensions. You can get complete information on the lattice, again, limited by the overlapping that comes from collapsing 3D down to 1D, and then the limit of the resolution of your instrument, which may lead to peaks which have a different D spacing being merged because the peaks are too broad. You can resolve a complete crystal structure, again with some limitations, and you can quantitatively measure phase fractions when you're in a scenario where you have multiple different scattering systems going on. But what about when you're between those two scenarios? And actually, this is the most common regime when you do high pressure diffraction. You can end up with it's not a perfect single crystal and it's not a perfect powder. It can be a non-randomized powder. It can be a textured powder. It can be a poor single crystal. So what can you do with that? You can actually do a lot. So you can still index in a lot of cases. You can identify phases and you can track them. So look at phase boundaries, look at kinetics. You can measure equations of state, and you can even look at strain in the lattice by looking at the widths of the peaks. But there's some things you cannot do. You essentially lose all information on the crystal structure, and that means quantitative analysis of mixtures, phase transitions is no longer possible because the information is not in the data. And then, of course, to make things interesting, the data themselves are not perfect normally when you measure at high pressure. So we have these main issues, background. So that could be either scatter from the anvil, scatter from the gasket. There's normally a pressure medium in there, which will also scatter. And very commonly, we'll have multiple phases as we use pressure to explore phase transitions. There'll be attenuation going on. So the anvil can attenuate the seat, the gasket. That's cleaner if you're using a monochromatic beam. If you're using a time of flight beam, as I'll touch on later, it actually can become very complex and non-trivial. We typically suffer from higher divergence as well because we're exchanging degraded divergence for a higher flux. Our samples are small and we need that intensity. And usually our signal to noise is poor, especially at high Q. And traditionally, signal to noise is bad for neutrons, but if you look at X-ray data from light materials, there's normally a very high Compton background, which is higher at high Q, which is high angle. And so signal to background can also be a challenge for X-rays. And it can't really be overstated, but it's critical to respect the limitations of your data quality and just not overinterpret where the information is not present. And I think this is especially important to bear in mind as we move into a world where we are going to start training machine learned algorithms to interpret our data. Those algorithms will be trained in some way, and they need to be trained properly to make sure they don't overinterpret our data. And I'm just going to flash one example up here. I don't know if authors on this paper are in the audience, and I apologize if what I say is controversial. But this is a paper from Nature Communications showing a Rietveld refinement of data, which, if you look on the 2D data on the right-hand side here, it's obvious by eye that this is not satisfying the necessary requirement of powder diffraction if you're going to analyze the intensities of having a well-randomized, untextured powder. So in my opinion, these data have been overanalyzed, and they pulled out quantitative phase percentages, and you can see these very precise R factors. Those are essentially meaningless because the intensity information is not in the data. So I just wanted to say that out loud, because unfortunately you do see a lot of this in high pressure literature. Anyway, I want to transition now to talk about neutrons. And whenever I talk about neutrons, I like to show this image, which is from a technical report by Robert Brugger from 1966. I still think, maybe people in the audience know better, but I still think this may be the first high pressure beamline that was ever built on a large source. It is a time of flight powder diffractometer, which at the time was completely, this was not the first ever powder diffractometer, but it was one of the first ones. And they deliberately exploited the time of flight technique because it allows you, as I'll talk about in a bit more detail later, to pull out a full set of diffracted intensities with a very low angular coverage of detector. And I also believe that the first ever fully quantitative powder analysis of neutron powder data by Rietveld was also done under high pressure. So there's this long history of neutrons being used under high pressure because they do allow the opportunity to do some things which are not possible with other techniques. This was the paper from 1976. So if anyone knows of a neutron Rietveld refinement before this date, let me know and I'll update this. So why might neutrons be interesting? Why might you be interested in doing neutron diffraction? Well, the most common thing which is said about them is that neutrons are able to see hydrogen. And this graphic shows the gray bars are the scattering strength of the various atoms and isotopes. And the solid line is showing the scattering strength seen by X-rays, which is, of course, is proportional to atomic number. So there are these advantages. When people say neutrons are able to see hydrogen, normally in the case of diffraction, they're talking about deuterium. So actually that isn't hydrogen, it's an isotope of hydrogen with double the mass of hydrogen. So it is a slightly different thing, and I'll return to that later. But you can play tricks with how there's this pseudo random variation of scattering strength for neutrons across the periodic table. So you can look at isotopic contrast, and for geoscience, this manganese iron one is quite different. These is quite useful. These scatter very differently, neutrons, but they have almost the same atomic number, so they're hard to resolve with X-rays. And then famously, because the neutron itself has a magnetic moment, it scatters from magnetic structures. And so you can actually do a Rietveld refinement or a single crystal refinement, and you can measure magnetic structure using neutrons. And this is where I wanted to make the point that to do all of these things, you actually need meaningful Bragg intensities. In the case of magnetic structures, you can identify magnetic phase transitions by just saying the magnetic peak is here, and now the magnetic peak is not here. That doesn't require accurate intensities, but everything else does. So it's very important to keep that in mind as you approach a neutron experiment and as you approach analyzing neutron data. So what do neutron data look like? And I'm going to, from here on out, focus specifically on powder data. And I wanted to reveal to you all Bragg's law for neutrons is indeed exactly the same Bragg's law as for X-rays, the familiar lambda equals 2D sine theta. And if you look at monochromatic neutrons, that also will look very familiar to people who have spent their careers looking at two-dimensional image plate or CCD data sets measured from monochromatic X-rays. And these can be integrated in the same way you would with a 2D image plate to give a pattern as a function of 2 theta. The only thing that looks probably a little bit odd is the Debye rings being extending out to such high angle that they become essentially vertical. This is about 90 degrees somewhere here. So this detector is spanning an arc rather than being a flat sheet as you would typically measure X-rays. But it gets a little bit more complex if you go to the time of flight technique. And the time of flight technique is using not a monochromatic beam, but a white beam. So the trick here is that neutrons are massive particles, right? They possess mass, and they, in the case of the neutrons we use, are non-relativistic. So the math is very easy. And thanks to de Broglie, we know that the wavelength of a massive particle is simply inversely proportional to its momentum. So this is Planck's constant. This is the momentum. The momentum of a neutron is just its mass, which is also a constant, multiplied by its velocity. And velocity is just distance divided by time. So here I use L to represent the total flight path distance, and capital T is the time of flight. So to make that useful for diffraction, you want to have a pulsed source. So that means at time equals 0, when you start your stopwatch, all the wavelengths are co-located in a single spot on the source here. But then as they travel along the beamline, they disperse in time. So that looks a little bit like this, which I hope comes across in the transmission through Zoom, with the higher energy neutrons accelerating beyond the lower energy ones. And then essentially the only thing you have to do is measure when the neutrons were made, measure when they were detected, and from that that measurement you extract their wavelength. So time of flight allows you to resolve wavelength, and that means if you have a powder, you get a full pattern, a full diffraction pattern in a single pixel. But actually, modern time of flight instruments have millions of pixels. So that is an extremely rich data set, but it's as a natural consequence of that, it can be challenging to process. As a nice vehicle to dive into some of the details of that, I wanted to introduce you to SNAP, which is the beamline I spend most of my time working on here in Oak Ridge. Here's a nice picture of the beamline looking upstream at the source. And this is actually a snapshot of some data measured on SNAP, but sliced, so we're only seeing a single wavelength. So this is the familiar Debye rings you would get with on a monochromatic X-ray source. This schematic shows some of the elements of the instrument. So coming from the left, we have the pulsed white beam. That passes through a focusing guide, which can be removed if we want. So that allows us to exchange divergence for flux. So if you want to have sharper Bragg peaks but lower flux, we can do that, or vice versa, we can also do that. The sample position is right here, and that sits on a hexapod, which is just a multi-axis but very high precision and high load bearing stage. And then about that same axis, we have 2 detectors, which in our case, they're called anchored cameras. A lot of this is shielding. You can think of the camera as being essentially a flat grid of active pixels, and each camera has 600,000 pixels. So we have 1.2 million in total. And then we have a nice online Ruby system, which we can translate in and out of the beam to check the pressure using Ruby fluorescence. We have quite a diverse range of sample environments, which we can plop into the instrument. So on the left here is the current iteration of diamond anvil cell. These were specially developed using funding from the first E3, and then I think probably the second E3. And this was very much led by Reini Bowler, who recently retired, but is still active in the field. And these have been demonstrated to exceed 100 gigapascals, and we've measured neutron data in that regime, which has been quantitatively refined to give meaningful structural information. Of course, we have Paris Edinburgh cells, which is a very traditional way to do high pressure neutron diffraction. These can get up to about 20 GPa, and we can run them at low temperature. We're in the process of thinking about elevating the temperature. And then we have the really traditional gas and clamp cells, which are available. Although again, with these, there are some specialities. Typically, a clamp cell will not go above 2 GPa, but we have a special one created again by Reini, which has been demonstrated up to 5 GPa. This is with a massively larger volume than you can get with the diamond anvil cell. So you can do different things with that. You can even do inelastic neutron measurements with this, exploiting that larger volume. And then finally, we would have the gas cells, which are larger volume still, but for those of you who may have worked with high pressure gas will recognize that this is 10 kilobar system, which we have is actually quite scary for high pressure gas work. And as far as I know, there are only 2 or 3 neutron facilities in the world which can operate up at this higher pressure. And I wanted to give you a kind of historical background on the development of the instrument. It's actually coming up on 20 years old now. I found the original proposal for the beamline, of which our chair was a co-proposer along with Dave Mao, John Parisi, and Chris Tulk. And that was way back in 2000. There were some initial workshops, a proposal was brought together, and then the instrument was built along with the spallation neutron source, which is itself at that time was a completely new source with a superconducting LINAC, a liquid target. These are all things which had never been done before. And that all came online around 2008. First users in 2010. And then the hardware continued to improve. They got a second detector. The guide was upgraded. The detectors were upgraded. And then just the end of last year, the entire facility got an upgrade from of the proton power source, which is getting us within spitting distance of 2 megawatts. We'd originally been running only 1.4 megawatts. So in this period of time, there's been a remarkable evolution of the neutron instrumentation. In parallel to that, as I mentioned, there was this very significant investment by the first E3 Energy Frontier Center, which was led by Carnegie. And over the approximately 5 years I was working in that, we really made huge progress in terms of implementing these diamond anvil cells. Some of that work continued after I left and went to Sweden in E3-2. And Reini Bowler actually transitioned to be an employee at Oak Ridge and was working full-time on developing pressure cells here until he retired. And now I want to contrast that with what has been going on with the software on the beamline. So when I first came here as a user in 2009, I think it was, the instrument was fully in the user program, but there was zero support at all for processing the data. We were basically given the data in an ASCII format and offered a the use of Excel to do all the normalizations and nuances that have to be done on the data. Sometime after that, a framework of neutron algorithms called Mantid became available, and some scripts based on using those algorithms to do some minimal processing of the data was available. But when I arrived in Oak Ridge in 2021, there was no automated reduction of the data. And just because it may not be familiar to some people, by the word reduction, what I mean is essentially processing of the data to remove all the instrumentation contributions to it. So it's going from neutron counts to something that's meaningful to a crystallographer, I call reduction. And that was an entirely manual thing. There were no user available corrections for the pressure cell effects on the beam, and there was really a lack of standardization. So depending on who the user was or who was running that day, you would get different types of data out at the end. And there's a very good reason for this, and it's that doing the software is very hard. And I wanted to just talk a little bit about why that's the case. So the first reason it's hard is because everything on the beamline moves. And that means that all the calibrations you have, all the knowledge you have about resolution of the beamline, all the knowledge you have of the wavelength response of the beamline, that all changes every time something moves. Trivially, if you move a detector an angle, then your Q range completely changes and your resolution completely changes. The other thing which I spent a lot of time worrying about is that the pressure cells themselves affect the data. And this plot here shows the transmission as a function of wavelength shown on the top axis of a neutron beam traveling through a diamond anvil cell. And you can see there are these specific wavelengths where you get a massive attenuation of the transmitted beam. And that, of course, reduces the number of neutrons at that wavelength that then Bragg scatter from your sample. And again, this would be relatively simple if you were doing a fixed wavelength measurement. You could just choose a wavelength here where nothing is changing. But the whole goal with time of flight is to try and exploit all of these wavelengths. So this was something that had to be considered. And of course, pressure cells also give you a large background. And essentially what I'm showing on the right here is a data representation of what SNAP sees. So these squares are the two detectors. The green axis is vertical, the blue axis runs along the beam, and the blobs are all the diamond Bragg peaks. And those have to be removed from the data so we can access the interesting sample information content. And then the last reason it's hard is because the data themselves are multidimensional. So what I'm showing here is a simple monochromatic diffraction pattern representation measured on a flat image plate. And if I now animate it to show how that would change if I could scan my wavelength to different wavelengths, you see essentially each Bragg ring grows as the wavelength grows. And what that means is, let's start that again, we get a complete pattern for each wavelength, but when we combine the wavelengths, we can get a single detector would see all of the Bragg peaks, and that's what we're trying to exploit. If I now show you how that would look on SNAP, so again, these squares are representing the data that's collected by the instrument. If I animate this, what I'm doing is I'm scanning through all the wavelengths that I have available. So you can see each Bragg peak is scanned in angle as I vary the wavelength. And I get all of this information for every single pressure point. And as I said, this is combining 1.2 million pixels. So just to give you a little bit more flavor for the complexity here, sorry, let me go back. One way to view this is that I can measure a single Bragg peak as a continuum of despacing across the whole instrument. But the problem is, or a complexity to be aware of, is that the resolution is changing as I go to different pixels. And also the minimum and maximum despacing is changing as a function of pixel. And then I will be honest and say if I tried to do an analysis of the data in a single pixel, it would be basically noise. So I do have to merge pixels together to get enough statistics to analyze the intensities. But how I merge them together is completely an arbitrary choice. I could do it in different ways, and typically the balance is the more pixels I add together, the wider my Q range, but the worse my resolution. So there are all these games that have to be considered, and adding that all up together means the analysis, even just the reduction, can become non-trivial. So this was something I embraced as my main task when I came to work in Oak Ridge, and it ended up being a software development project, which we call Snap Red, which is snap reduction. So the high-level requirements is that a user who is not a neutron expert would have frictionless access to analysis-ready data, could go straight into standard read-build analysis code. It was going to standardize all the calibration and the reduction workflows, and we would retain full provenance of the data processing. So if one user reduces the data and they get a data set, a different user would be able to exactly replicate every step in that and make an exact copy of the same data by following those same steps. A little bit about resources. So this was my full-time job for about 3 years. And the model for software development we have in Oak Ridge right now is interesting in and of itself. We have professional software developers. Some of them are scientists, some of them are not scientists, and the scientists we have may know nothing about neutrons. So this was a very interesting project where I learned a lot about communicating with software developers, and the product which came out would not have looked how it does look if it had been created solely by scientists, I believe. There's a lot of tricks that professional software developers know, a lot of things they're aware of, which I would say most amateur facility scientists, neutron or X-ray scientists may not be aware of. And then we exploited also this Manted framework, which has existed, I think, for over 15 years or so now, which is a really nice example of multi-facility collaborative work to create algorithms which are useful for everyone. And that saved us an enormous amount of effort. It still, despite that, required an enormous amount of effort. So we kicked off the project in 2022, and the user-ready code was finally deployed in 2025. So it's been running for a year now. Those of you who are aware of overheads in national laboratories might want to pause and think about how expensive 5 FTE running over 3-year piece of software was to create. A little bit more about what we made. The entire code is open source and on GitHub. You can go to this web address and look at everything. We had 15 total contributors to the code base and 840 commits. And essentially the 3 things it does is diffraction calibration, which is the conversion of time of flight to despacing. The normalization calibration, which is correcting the wavelength response of the instrument, and reduction of data using those 2 things. And an important element of the software design, which was one of the reasons it was so difficult to create, is a high-level requirement that the end user only needs to know their run number. They don't need to know. So run number is a label for every exposure that's done with the neutron beam. That's done automatically. And a user would know that. They do not need to know where the detectors are, whether the guide's in place, or any of those details. They just need the run number, hit enter, and then they get data they can analyze. And I don't spend too much time on it, but because it's been such an important part of my life for so long, I wanted to give a few details about how that actually works under the hood. Um, we had to define the instrument state, which essentially we do by tracking the values of a specified set of process variables, which are things which are logged automatically whenever the neutron data are collected. Things like detector angles, where the incident wavelength band is centered, whether the guide is in the beam or not. These are all logged in the neutron data as process variable logs. And then we take the values of those logs and convert it to a simple 16-digit ID number. And then we create a folder with that same ID number. And that's used to orchestrate all the workflows. It allows the reduction to find the appropriate calibration data and to link it to the specific neutron data that's being reduced. We also support ways to combine these pixels. So generically, that is via pixel groups or pixel masks. And just to kind of make concrete how this allows us to take this multi-dimensional data and make it easy to analyze and process, I've again got my little 2-square representation of the instrument here, each sort of larger square representing a detector. And then within that, the 9 smaller squares, 3 by 3, are individual modules within a detector. And the color coding is encoding pixels that have been told you're in the same group. So like all the pixels in the yellow, colored in yellow here, these are all being added together into the same diffraction pattern. So if I group them in this way, and you can see I have 6 different colors, that gives me 6 different spectra, which I'm showing here as a function of D. And so you immediately see the complexity because the groups, individual groups are at different angles. My D spacing range is completely different for each one of those. And if this image on the right here shows a zoom in to the peak here, and you can see the resolution is also changing. And a tiny detail I'll emphasize, because it cost me maybe about 4 months of my life, is the software is automatically selecting the appropriate binning. So the spectra where the peaks are broader, the histogram bins are wider apart. And that means whichever Bragg peak you're looking at, it's being sampled this with the same resolution. And that's important for doing Rietveld analysis. And then finally, it also supports arbitrary masking of pixels and regions within pixels. And here's like this shows a typical mask which has been applied to remove those diamond spots. And just to underscore the binning and the histogram minimum and maximum limits, that's all recalculated on the fly to respect any masking which is done to remove pixels, because that would remove the weighting of how the conversion from time of flight to D-spacing happens. Finally, what's also available is more or less fully automatic corrections for the cell-specific stuff. So in the case of diamond anvil cells, all of the complexity I mentioned with is all now running under the hood. The user doesn't need to be aware of it. And shown on the right here, a lot of the data I'll show is unpublished because this was only rolled out at the beginning of this year. But this is, on the right, a diamond anvil cell data. It's, you can see on the scale here, this is 0 count. So this is true signal to background. And every peak here, apart from this one, which is coming from the gasket, is from the sample. And this is a hydrogen-bearing material. These are fully quantitatively analyzable data sets, which is something which previously would have taken weeks, maybe months to achieve. And now it's coming within minutes if you're starting the beam time. Yeah, and this has been running for since the beginning of 2025, so it seems to be working really nicely. So just a small plug then for the Snap beamline. So Snap is very much a full service beamline. I'd like to think that anyone who comes to do an experiment on the beamline will be happy with how the experience. So we're doing cell preparation. If you provide sample, we'll put in a diamond anvil cell for you. The instrument calibration is all going to be done for you. And we can offer real-time data reduction, support with the Rietveld, and the data archiving and cataloging all comes for free. And so just to round that out, I wanted to show some recent science which has come off the beamline, just to underscore some specific capabilities which I think may be of interest. So this is some work by Chris Ridley, and it kind of shows the very much bread and butter fundamental benefit of being able to do neutron diffraction. So these are actual crystallographic measurements involving, in this case, a bond angle with a hydrogen atom, a deuterium in this case, as a function of pressure. So if you want to pull out that exact structural information, in particular, if you have light atoms, this is a very much what SNAP is made to do. This is some work which is from Yogesh Vora's group, looking at gadolinium compounds. For those who don't know, gadolinium is a massive, massive neutron absorber. So this shows a transmission as a function of sample thickness. And essentially, if your sample is more than 100 microns thick, you don't see it anymore. Yet on SNAP, we are able to see these nice diffraction patterns because we are so well optimized for looking at small samples. Well, small, in the case of neutrons, this is a very, very microscopic sample. Yes, it's probably still large for synchrotrons, but when you get down to 100 micron type levels, that's still, I think, impressive for at least for neutrons. And then, of course, is the work of doing Rietveld in a DAC. So this is it's a measurement of nickel, but what you see on the bottom here is a full Rietveld refinement at 100 GPa of a sample measured in a DAC on SNAP. And this is not putting in weird and wacky 10th order spherical harmonics, texture parameters into the refinement. This is just the pure structure and demonstrating that the intensities which are coming out are meaningful. And this particular paper was an example of one where it did take me weeks to get all these intensities properly corrected for the effects of the diamond cell. And this can be done now in minutes. And I don't have any data to show you because we're still analyzing this, but we've discovered that we can actually measure hydrogenous stuff instead of deuterium. In particular, if we look in a DAC, it turns out, for those who don't know, if you hit hydrogen with a neutron beam, you A, get huge absorption, you B, get massive multiple scattering, and C, you get a huge background. Turns out if you make your sample really, really small and really, really thin, most of that goes away. So we've been, unfortunately, I can't say what it is right now, but we've been looking at very hydrogen-rich samples, more than 50% hydrogen, and it seems entirely tractable. So we're super excited about this because A, it's often not possible to deuterate your sample, and B, quite often the physics is different if you're using hydrogen instead of deuterium. So that's something we're very excited about. Should you want to do an experiment on SNAP, another thing which is we've been pioneered by Chris Ridley is a mail-in program. I don't know if another high-pressure beamline that's yet doing a mail-in program, certainly in the neutron sphere. And you can put in a proposal anytime by going to this website. If you click on this button, you'll see all the details. It's currently limited to Paris-Edinburgh cell measurements, but this is an excellent way to get preliminary data on a system which you think might be interesting to measure with neutrons. And then there's, of course, a general uh, proposal call, and the next deadline will be early next spring. Here's the current team. We've got Antonio, Chris, myself, and Jasmine Hinton. You feel free to contact any of us if you have any interest at all in doing experiments on Snap. So I have a little bit time left, and I wanted to kind of building on the description I gave already of the diffraction data we have, give some personal thoughts about what we need to do next. So an unavoidable truth about high pressure diffraction, which I've been doing for a while now, is that we're always going to have imperfect data and we need to maximally exploit that. And one clear opportunity to do that is to retain its dimensionality. So in the case of monochromatic beams, they're intrinsically 2D. In the standard measurement where you have a single wavelength and a 2D detector, you get these 2D images. And very commonly that will be integrated up to a 1D pattern, and then that's what gets saved, that's what gets published. But there's a rich source of information in the 2D data sets. So you have the spottiness, which is nicely illustrated by this image I found here of increasing crystallite size. But there's a lot of other detail in there, that there could be trends in peak shapes, there could be textures. And I think so to quantitatively assess if it's even feasible to analyze intensities, you should be analyzing the 2D thing first. B, if you want to resolve multiple phases, so this ring is from phase A and this ring is from phase B, I think you want to be interpreting the 2D information. And why not just do all the analysis with 2D? We have powerful enough analytic computational codes now that that's absolutely possible. And then, of course, the best example I can give of this is the multi-grain single crystal diffraction, which is happening now. This is excellent because it allows you to pull out the full analytic power of single crystal diffraction, but do it in multi-megabar regime. So this is extremely exciting for me. In the terms of neutrons, so as I hopefully explained in a clear way, we have this three-dimensional data. We've got the extra dimension on top of what you get with the monochromatic beam. And currently we're reducing it to sets of one-dimensional data. And from my own experience, a practical limit on that is 5 or the 6 histograms I show here. But there's no reason I should limit it to that. It could be 100 histograms or more. And I have that for every single pressure point or every single temperature. So I may have thousands of these data sets, each of which has hundreds of histograms. And I'm convinced that that cannot be analyzed using traditional Rietveld approaches. And given the rise of large language models, I think there's real scope to develop a AI-assisted Rietveld analysis. You know, my dream is kind of, you can ask, please, ChatGPT, please do the refinement, and it will go off and it will let you know about a little cluster of histograms where the phase profile parameters are not tied down, and it can intervene and it can lock down parameters and that way guide you to end result and let you know what's going on with the refinement. And why not split that into 10 different parallel processes so you can strategically explore different avenues through the refinement and find the optimum one. I think there's an enormous potential for developing that in the next few years. And then I just wanted to round off by talking about metadata. Now, just in the last week, this announcement came out about the Genesis mission, and part of that is the American Science Cloud. And a big idea behind that is to link together the data, which the enormous reservoir of data which the DOE creates through its large-scale scientific facilities. And they mention here exploiting DOE's extensive AI-ready scientific data. And I had to ask the question, if we're AI ready, Um, and in the case of Snap, if I look at where we're at now with the way we're processing our data reduction, we're not bad. We have a standardized reduction workflow. We have acute quality assurance on the calibrations. We have data provenance, and we have archiving cataloging. What's missing is the metadata. Um, it's not missing, but it's known that there's need for improvement. And I actually was aware that Camille Zurbeck has been pushing for some time now a CIF-based standard for capturing the metadata associated with loading diamond anvil cells, like things like what equation of state were you using, what was your calibrant, what gasket did you use. But I don't know how much this has caught on, and unfortunately, CIF it's quite an old-fashioned standard. I think there are better ways it could be done now. I'm currently, with the help of the Snap team, developing an approach on Snap, which I'll share now. This is still, let me go back. This is still developing, but I think there are elements here of what we need to address this AI readiness requirement. So already our system in neutron sciences here is if you get allocated beam time, you'll be given a number, an ID number called an IPTS number. And then as you collect your data, every single exposure is given a unique run number. That's these numbers here. And the corresponding neutron event file, which in addition to the events contains all of your process variable logs, temperature, hydraulic pressure, things like that, inside the data file, and also a full instrumentation model. It's all inside the file, and that's stored in a folder inside your IPTS folder. Now, when we run our snap read to reduce the data, that's automatically spitting out into the same folder in this location, data which are ready to go straight into GSAS, FullProf, Topaz, these standard Rietveld analysis codes. We also spit out a reduction record, which is a full captured, captures all the details of the reduction, and there are a lot, which is all under the hood for typical user. But if there's any question about a detail of that, that can be dug out of this record. And then we're creating a metadata folder, which we are instantiating in there JSON serialized files recording sample crystallographic data, cell loading data, such as gasket material or stuff. And then finally, any auxiliary data is going in here as well. So Ruby data, photographs of the sample taken through a microscope, Raman data could all go in here. And what's powerful about this is we can version it and we can expand it. So let's say when I do the loading, I think I have a material, I'll choose a random material, D2O in my diamond anvil cell, and then I do the refinement and I discover, oh yes, there is ice in this sample, but also we're clipping the gasket a little bit. So there's some tungsten in there as well. I can update the information in this sample thing and say, now at this point in time, I know I have ice at this pressure and I have gasket at that pressure as well. And so as your knowledge of the system evolves, you can update the metadata. And we also have the capability to mint a DOI. So we can publish this entire thing and we can link it to a publication. So you're really sort of addressing this need to have all the background information for a given experiment, which, so A, any reviewer could ask for this stuff, and B, an AI could ingest it. And let's face it, if you Google the American Open Science Guide and say, give me all data on silicon that has ever been measured at any national lab, it's kind of important to know if that silicon was measured at 10 GPa or ambient pressure. So I think hopefully this is going in the right direction to prepare us for that. So I'm just going to wrap up here with a very quick summary. I think there are significant new opportunities on STAT now coming into 2026. We've had this enormous improvement in our technical capability, and now finally that's been matched with our software capability, and it's been kind of put into a package which I think is very user-friendly and accessible, and we very much welcome anyone who's interested to do an experiment with us. The issues of the data reduction have been more or less solved, so you don't need to be afraid of coming in and working to do a neutron experiment and at the end being left with data that aren't actually that usable. And then finally, it's absolutely not an answered question, it's an open frontier. I think there's still a lot of richness in these time of flight data sets, which is not being exploited simply because we don't have the software to do it yet. And that probably looks like some kind of AI assisted or even AI led analysis of the diffraction intensities. And so I think there's a great potential to grow that in the very short time frame of the next few years. So just to wrap up, some acknowledgements which are hopefully are mostly comprehensive. Again, to acknowledge the people who originally wrote the proposal that led to the beamline being made, the invaluable contribution by staff funded by E3, the contribution of Oak Ridge and the contribution of the SnapRed team. There's a lot of guys put a lot of effort into creating this software. And of course, I have to acknowledge the DOE is funding my own efforts in the endeavor. So that's everything I have for you. If there are any questions, I'd be very happy to try and answer them.
Thank you, Malcolm, for a beautiful talk. It's really valuable work, and I think the whole community owes you a big debt of gratitude for what you've spent the last 4 or 5 years doing. This is a heck of a lot of work, so congratulations.
I appreciate you appreciate it, because if my work's been successful, then my hope is that most users will not notice it and they won't appreciate it. They'll just type in the run number and their data will fall out. And if that happens, I've been successful.
Okay. Well, we'll direct them to this talk, which is recorded, so that they know the background and what's under the hood, as you say.
Yeah.
Okay. The talk is open for questions and comments. Brent.
Thank you. That was really a good use of my time, Malcolm. You were succinct and very clear and up to date. So thanks again, as echoing Russ. I'm wondering, is your planning ahead for using the Paris Edinburgh cell at higher temperatures? What are the limitations here? Are there any particular components or ranges of temperature you're aiming for?
Yeah, so the main limitation is the anvils are supported by binding rings. And as they heat up, then they don't support anymore. So you have to be very careful to thermally isolate the sample from the anvils that contain it. And this has more or less been a solved problem up to, I think, around 1600 Kelvin. It's been demonstrated at ISIS. And at least up to that regime, it's purely a question of resources and getting it implemented. It's achievable. I should also say there is interest in exploring laser heating, and that's ongoing here. But we haven't got to the point yet where we're able to put that into the user program. It's something Riney started working on, and then he retired, and so it's not ready yet.
Thanks very much. Anmol.
Hi, thank you very much for the talk. I have one small question and a few comments.
Yep.
I checked out your the program, and the GitHub is very impressive work. Seems very useful. I haven't used the Beamline yet, maybe in the future, but
Yep.
seems like very user friendly, and you even have like IDE support. I also saw GUI.
Yep.
I don't know if you have proposed improvements on that. And yeah, and next thing was my question was that your instrument state, is it something that requires a little bit involvement, or is it like more automatic?
It's very automatic. So a lot of most things you can do just remotely. Changing the detector positions, you still have to go and do that in manually, but the positions are detected and then they're logged. And so once the software processes all that automatically.
Awesome. And then I also like really love the idea of the handling of the metadata and changing the data structure. I
Yeah.
think great idea to use the SDFI file format,
Yep.
and we're looking forward to what's gonna happen with that.
Yeah, we're actually using HDF for our the reduction record I mentioned. That's all HDF format. Currently, a lot of the metadata is stored in these JSON serialized format, but that also could be bundled into HDF. And so there's no reason you couldn't have an entire experiment as one HDF file.
Right. No, that would be awesome. Awesome.
Yep.
Thank you.
Yep.
More questions, comments?
Oh, is there any chat?
Okay.
Oh, somebody found an earlier reference to a neutron Rietveld refinement, 1969. Thank you for that.
Okay.
So that was a direct message to me. So maybe the others didn't see it, but great. That knocked like 10 years or so off the record.
Yeah, thank you. So I have a question, a technical one regarding using different diamond cells. I can imagine, different cells are going to have different shadowing effects.
Yep.
So there's sort of a standard set of cells you use for some of your diamond cell diffraction studies, but if you have different ones that shadow differently, how do you take
Yes.
that into account?
So two quick responses. So we're actually figuring out the orientation matrices for both diamonds automatically in the background. And from that, I can calculate the affected wavelengths and I can process them. It turns out so we have gone through several different suppliers of diamonds, and when those were being procured, we weren't worrying too much about the alignment of the diamonds. But what we've realized now is actually it pays us enormous dividends to get the unit cell axis of the diamond to be as close as possible to parallel to the beam. It cleans up the distortion of the wavelength and makes a lot more of it usable. So those are commercially available. We have an order in to get these better aligned diamonds, and that should, in addition to giving us more wavelength band, it will make them more similar to each other.
I see. Okay.
But either way, that's another thing we're tracking. So we just sort of track the orientation of the diamonds with every measurement we make.
I see. And if you show up with your own diamonds, you should know the orientation of the diamond relative to the cut then.
We get it for free from the diffraction.
But
But
you measure it there.
if you
on the
show up
fly.
with your own diamonds, there is still this limitation that your pressure cell may become radioactive. So this is why we're trying to do more of the full service thing where we do the loadings here. And as you can imagine, that's quite a lot of work, but it's a way to solve that problem.
Great. Okay. Christoph, go ahead.
I can't hear Christoph.
Christoph, you're muted. We're still not hearing you. There you go.
Maybe if the microphone's not working, you can type a question or
Oh, yes,
comment.
he used the chat. How well can you control temperature during high pressure, low temperature data collection?
Okay, so it depends on the pressure cell. With Paris Edinburgh cell, uh, we, we're actually working to improve that. In the worst case, it can be quite bad. It's like plus or minus 10 Kelvin, and we're currently actively working on getting that down to a smaller number. For the diamond anvil cell, it's pretty good. It's around a Kelvin. It's just bolted straight to the cold head of the CCR.
Right. Okay, thanks. Since I have you on the stage, can you tell us the latest on what's happening on the second target station front? Where does that stand? And the plans for next generation high pressure uh, diffractometers and the
Right.
next generation of SNAP?
So, if I look out the window on the other side of my office, the ground has been cleared. The forest is gone, and they're actively working on preparing the site. Um, I think there is some rearrangement in terms of the project structure, but most people I speak to believe it will go forward at this point. In terms of the diffractometers there, I was actually a little bit disappointed when I saw the designs because they're kind of quite conventional, and the focus is more on kind of higher throughput, and still putting the detectors inside these enormous vacuum tanks, which make any pressure work much harder. Um,
Hmm.
I really think if I had the opportunity to create a new beamline on the second target station, it would look something not dissimilar from Snap. It would have a lot less moving parts, and it would have larger angular coverage, but it would still be hands-on accessible, and it would still retain this single crystal, very small, high resolution pixelization of the detectors. It's critical, A, to deal with your diamond spots, but also when your sample may be a single crystal, or it may be a powder, or it may be one or the other, and then change during a phase transition or something in between, you really need that flexibility in your diffractometer to hold it, to handle that. And because of this classic neutron design, where I think all the other high pressure neutron diffractometers in the world, apart from maybe Dubna, have this sort of fixed 90-degree geometry, it does not give you that. If there's any texture or preferred orientation, you can't really quantify it. So it would look like a amped up snap, probably.
I see. Okay.
And just to close out on that, I believe there are discussions about building a high pressure beamline at the ESS now as well. That's not decided yet, but there are ideas to put a proposal in. And that, of course, is not currently in the suite of detectors at the ESS.
I see. Okay. Well, we're well past the hour.
Yep,
Thank you
sorry
all
about that.
for joining us. And Malcolm, thanks for a terrific talk.
You're very welcome, Russ.
Okay. Happy holidays, everyone.
Yep, thanks, everyone.